Hi, everybody, and welcome to the first iteration of the Spectral Geometry in the Cloud seminar for this winter term. So today we have the pleasure of having Oleksiy Klurman from the University of Bristol, who will talk to us about boundary adapted arithmetic random waves. As usual, if you have questions during the talk, don't hesitate to just unmute yourself and ask them as the talk goes along, or to ask them in chat and we will relay them to the speaker. So Oleksiy, the floor is yours.
Oh, thank you very much for the invitation. That's, of course, a great pleasure for me to speak in this seminar. The immediate disclaimer here is that this is essential. So I'm not a spectral theorist, and I'm a number theorist. And usually my exposure to the random waves is very tangential. But the problems that I want to talk about is I want to focus on is there's some certain number theoretic problems which have been studied separately in the number theory context. And then there is this nice mix of them to appear in the context of the random waves. And well, my knowledge in the random waves is not particularly great, so I very much hoping that you can teach me. But so the number theory questions that I want to focus on is So the number theory questions that I want to focus on are very, very simple question to state. And this is a question which is called the tricky problem, because Bombieri gave a talk about this in the Institute, and he calls it as a tricky problem of the sum of two squares. So what is this type of questions that I'm going to be interested in? So the type of question is very, very simple. So suppose I give you a circle in the 2D circle. And well, you can think about that as having integral points there or not integral, but suppose I have a bunch of points on them, on the circle. And suppose they happen to add, when I take these points, they happen to add to 0. So, and the basic question that I want to understand, so I wrote here 6, but there is nothing special about 6. So you could take 200 points of them. For me, I'll stick to the even case. And this question is very basic. So why 6 here? So one, if we think about that, so the first non-trivial case, you could think about the adding 2 points to 0. And if you add 2 points to 0, then of course the only way to get it is one is symmetric to each other. So the only solutions to such equations are a equals to minus b. So there is a symmetry. This is not really a big deal. But if we take already 4 points, so this is a nice observation which goes back to Zygmunt actually 100 years ago, is that if you have 4 points, so how many solutions to such equation when they add up to 0? And one way to think about that, to get the feel of the problems that I'm talking about, is what you can consider if you write this equation as a plus b equals to c plus d, then as soon as you have this, the left-hand side is fixed, as soon as you have the sum of the two vectors is given, then there is only a unique way to decompose it as a sum of the two unit vectors. And what you would do is you would take just the circle of radius with of radius 1, and you would just recover these points. So if you look at the 4 points, the only way they can add up to 0 is that if AB is equal to if minus C minus D up to some permutation. And that is the observation that has been made 100 years ago by Zygmunt in the context of norms of the Fourier series. And so this is the reason why I wrote 6, because 6 is the first non-trivial case. And this is the problem that has been considered by Bombieri and Bourgain. So what is the number of solutions to such equation? And what they conjectured is actually that, so here is the conjecture. So what they conjectured is actually, so I'm going to stick right now only to integer points on the circles. So I'm going to take the circle of radius square root of n and take the integer points on them. And so what they conjectured is that the only way to get, essentially the only way to get the sum of them equal to 0 is that if you take 3 of them, you fix 3 of them, and you take another 3 to be minus these points. And they, of course, there is this epsilon here for safety, but really this is, the conjecture is that the only way to get these solutions, the main term comes from the diagonal solutions. And well, this is the interesting question on its own because it concerned the additive properties of the points, but they have tried, I mean, they've done wonderful work and they've used a variety of different techniques to attack this problem. So techniques from combinatorics, and that gives us the best unconditional results of such problems. So namely, instead of epsilon, there is exponent 1/2, which you can put there in terms of the solutions. And they tried, they also considered the Diophantine approximation properties and proved that this conjecture holds for some certain families of n's. Arithmetic geometry, they reformulated this question in terms of the, if the conjecture is false, then some number theoretic conjecture about the rank of elliptic curves, they happen to be unbounded. And the methods that I will talk today about and about the problems, they are related to the last two, the statistical methods, and what can we say about most of the circles. So this is the problem that also arises in the study of arithmetic random waves, and I'll come back to that in a minute. But the problem that one can consider, and I want to consider, is more general one. So in the more general one, the motivation is the following. So now suppose that if I give you 10 vectors, each of them of length square root of n, and if you add them up together, then the length that you expect to get of the vector is also proportional to square root of n. If there is no non-trivial relations, then there is no reason to have a cancellation. So the second sort of problems that I am interested in is related to the following question. So now suppose that I've given you the points, and suppose that what happens is that when I add them up together on the circle, I don't quite get the perfect cancellation, but what I get is that the, what I get is that this main term, the sum, happened to be shorter than it should be. And exactly the same question, what I want to ask is that what is the cardinality of this set and when can this happen? So when can this happen? And remarkably, this will also happen only when the sum essentially equals to 0. So, and this problem has been, it's already a non-trivial problem in the case even k equals to 1, and it has been considered in number theory community and also in random wave community by the people that I mentioned, Bourgain and Rudnick and Granville Wigman, and so on and so forth. But I will talk about this a little bit more.
Oleksiy,
yes.
Just a small remark. In case when vectors add exactly to 0, if you restrict n to be powers of fixed prime, or if you fix the prime divisors, then essentially there is some uniform bound.
Right. So so in Diophantine approximation case, it's exactly what is considered, and so primes has this rigidity. We'll talk about that. Has rigidity that it only has 4 points. So you exactly know, you're absolutely right. You exactly know where the points arise. And in the Diophantine approximation case, in general, if your integer is composed from small number of primes and raised to the high powers, there is a very rigid phenomenon that happens.
Right. And also, I mean, you don't, this can be not just for 6 vectors, but for 8, for 10, for any number.
Exactly. So all the 6 I chose here only because this is what the first non-trivial case, and everything that I'm going to be talking about is valid for 2k points, and that's what we need. So that's okay. Absolutely fine.
Great. Thanks.
So yeah, thank you for the question. Okay. So right. So this is, and finally, the problem that even more, so this type of questions, if you think about spectral theoretic part, it arises where you study the quantities in the shrinking balls in the context of the Planck scale equidistribution. And finally, what I want to talk about today is the third type of question, even more general. And this is the following question. So this is the question now. Imagine that now, instead of I relax the previous condition, and now what happens is that I have a direction. So if you think about the randomness phenomena again, if you fix any direction in the unit ball, then you would expect that if the points do not collide, then the projection on any direction has to also have the size roughly square root of n, if there is no degeneracy. And this is the question what I want to consider as well, which is what happens if there is a direction on which the projection happened to be smaller than the expected one. So if you're bored with everything that I'm going to be talking about afterwards in this setup, you can try to think about these sort of questions and play around with that. But this is what arises when studying the nodal quantities with the bound, for manifolds with the boundary. So now I will go to the setup and try to explain where does this problem arise, and then in the context of random waves. So the setup that you are very much all familiar with is that we gonna work in the space on the compact manifold, and Laplace, there you can define the Laplace-Beltrami operator. I will very quickly move to the Taurus, even to the Taurus. But as a general setup for the Laplace, of course, operator, you have a space of eigenvalues, which form eigenfunctions form an orthonormal basis. And for typical manifolds, the multiplicity of each eigenvalue is, of course, 1. However, the cases that I will be considering as a case of Taurus, there you have a multiplicity which is rather high. And the quantity that people in this community study a lot in your community is, of course, the nodal lines. So this is the level set of your favorite eigenfunction. And the nodal lines, they are generically are smooth curves, so you can rectifiable curves. So you can talk about the length of this level set of the eigenfunctions. And the goal that one would pursue here, at least, is what is the behavior of the nodal line when the energy levels goes to infinity. And of course, you can study a lot of quantities associated with the nodal lines, but the most basic one is the length of the nodal line. And I put here before a lot of names that people that worked on that, and then I commented out because my lack of knowledge in this literature, I don't want to miss any people. So an enormous amount of people, of course, have worked on these problems. Yeah. Let me not mention specific ones, but let me just have here what we must have is the picture, and which I stole from Dmitry Belyev's website. So this is the nodal lines and nodal curve. You can see the of the random spherical harmonics. And so what you can see immediately here, so the nodal lines is exactly the boundaries between the white and black regions. So this is where the eigenfunction is positive and negative. And you can see that there is a lot of complicated structure here, in particular about the nodal, how many connected components are there, and so on and so forth. So these questions have been studied a lot. So what I will be, as I said, I will be interested in the nodal lengths. And so what about the nodal length? So if I don't talk right now about the randomness, then of course the guiding conjecture here in the field is that the nodal length of the eigenfunction with eigenvalue lambda should be roughly commensurable with the square root of the energy level. And this is a notorious problem, and with the spectacular recent breakthroughs by Logunov and Malinikova. So the case of this problem for the smooth case is rather difficult, but even this question of nodal length is very, very difficult. So, and to overcome this, in some sense, difficulty, Berry proposed to study a random version of such questions. So what is this random version of the question? So Berry proposed in 70s the model which models the generic eigenfunction on the generic manifold. And there are several ways to define it. And one way to define it is well, what one can consider is this nodal. So take your favorite frequencies. So take your favorite frequencies, random which are uniformly distributed on the 0 to pi. Take your shift psi, which is also independently uniformly distributed on 0 to pi, and take the superposition of such waves. So one can check that it satisfies on the plane now. So I'm talking about R2, and on the plane, it's of course satisfies the Laplace equation, but it's not defined on any manifold. And another way, so this is the physics community prefers this definition. And if you talk about the probabilistic community, then the definition, one can define it alternatively via define the central Gaussian field. And Gaussian field is given by the covariance, where the covariance of the random Gaussian field is given by the value of the Bessel function. So what is important here is that this is a stationary random field, and which means that the covariance matrix only depends on the distance between the points x and y. So it does not depend on the position of x and y, but only on the distance. If you prefer not to think about the random fields, then I will very quickly define some very concrete object in the case of the torus. So this is the random model, and what Berry suggested is in 70s, in fact, is that to model, so the philosophy, I don't call it conjecture because I don't think there is a precise, at least I'm not aware of the precise statement, but the philosophy is the following, that if you want to understand every eigenfunction on a generic manifold, chaotic manifold, then one can model it by the typical eigenfunction, the quantity. You can model by the typical eigenfunction from the ensemble that I just described. So in particular, you can compute something there. And this random model, of course, in the physics community that has been used for the predictions, in particular Rice, which is from Katz-Rice formula, and Higgins and Longwood, they used it for the prediction of the ties of the waves, and has been used in the detection of cosmological data as well. So there are these very nice pretty pictures that I don't understand much about, but the model that I want to describe, I just want to describe this particular model in the case of the torus. So, or rather, first, before I move to the torus, let me say what this model tells us about the nodal length. So what you could do is you could take the typical function that I've just described before, and you can take a rectangle in the R2, and you can look at the random variable, which gives you the length of the nodal line of this eigenfunction of the zero set. And Berry computed it several in 70s, I guess even. So what he computed is that actually the nodal length, the expected value is proportional to the square root of lambda, what you expected. And of course, this is good news because it's consistent with the Yau's conjecture that it has to be. If you got not square root, that would be a problem. So this is not a surprise, but surprise which happens about 20 years ago is that when he computed the variance happened to be of the order of log, which is not what you expect before, because if you done the calculation before, you would expect the variance to be much, much bigger. And what he called this in about 20 years ago, he called it an obscure cancellation phenomena, whatever obscure it means, claiming that the sort of source of this cancellation is unknown. So for some reason, this nodal length is very much concentrated around the mean. And so at 20 years ago, it has been unknown, but so I will mention right now a couple of results. So this cancellation phenomena, which is called random cancellation phenomena, has been over the years spotted in several ensembles. So one in 2010, Igor Wigman has proved it in the case of random spherical harmonics. And in 2019, and well, paper appeared 2019, actually even the central limit theorem has been established in this context. And in random, roughly the same time, in the case of arithmetic random waves, this is what I will be caring about, that has been noticed by and proved by Krishnapur, Kullberg, and Wigman. And again, in 2016, it was the central limit theorem, non-universal central limit theorem has been established there for the nodal length by Marinucci, Peccati, Rossi, and Wigman. And very, very recently, in the context of really the Berry random model, the central limit theorem as well. If I have time, I'll talk a little bit about that. But the central limit theorem and this cancellation has been in some way, at least in probabilistic way, explained where it's coming from in the papers of Nordin, Peccati, Rossi, Peccati, Vidotto, and so on and so forth. Again, I do apologize if I missed the names, but this is just a lack of knowing the literature. So what is this random Berry's cancellation phenomena? There is not precise definition to me, at least, but I think if you compute the variance and you are surprised that it's small, it's called the Berry's cancellation phenomena. In this, at least this is my take on it in this regimes. Okay, so now I want to talk about the torus. And the torus is a 2D torus even, and the torus is a very specific manifold. So what do we know about the torus? So the typical, the eigenfunction, the eigenvalues are given, they have an arithmetic structure, of course, and the arithmetic structure is given by, So the arithmetic structure is given that the normalized eigenvalues, they happen to be integers. And not only the integers, but the integers representable as the sum of two squares. So the basic eigenfunction, this is your harmonic. My iPad doesn't want to do what I want it to do. So, and what we can define in this case, if you forget about random fields, you can define a very, very specific and particular eigenfunction, which is the, so what you do is you take a superposition of the basic eigenfunction with the Gaussian coefficients. So this is exactly explicit definition of what I've been talking about before. So this is the arithmetic random wave. So, and here you sum up your points mu over all eigenvalues over all integral points on the circle. So for this to make sense, you need to have the sum to be quite long that you enter in the regime of the central limit theorem. And luckily, this becomes a beautiful arithmetic problem. So let me tell you a little bit, whatever I'm sure you know, but let me tell you a little bit about, introduce a little bit more notation. So for this random eigenfunction, we can define this covariance that we've talked about before. It will take a very nice form that you can see here. So R of M, this is just the covariance matrix. Then we don't actually need to think about that at this moment. But what we do need to understand is this is certainly the what is the dimension of the eigenspace that we consider? How long is our sum? And this is a very classical question in number theory. So this has to do with the number, of course, of representation of n as a sum of two squares, right? And so what we know is the result that goes back to Landau is that if I give you an integer m, there are different things that might happen. So some integers, if you want to represent integers, oops, I don't know why, sorry, my iPad doesn't want to listen to me. But if you look at the number of representations of integers as a sum of two squares, then there is a beautiful behavior. The behavior is very erratic. So on average, for typical integer, it's got square, or rather on average, there is a square root of log m representations of, so the number of points on this circle is power of log. It's not quite square root of log, it's on average square root of log, but for typical integer, it's still a power of log. And so this is, the eigenspaces are rich, but some of the eigenspaces are very poor. And in particular here, there is something which is, if we look at the prime, and if we look at the number of representations of integer over the prime as a sum of two squares, that there is essentially unique representation up to the rotation. So namely, there is a unique representation, and then of course you can take points of the form plus minus m and plus minus n plus minus n. So what happens is that for the primes, this eigenspace is extremely poor, but for the typical integer, it's quite rich. And that's why it allows the central limit theorem regimes to kick in, because it's quite a rich eigenspace. I will talk more about the points, but let me just, for this model, I'll come back right now to describe more information about the points if my iPad is working. Okay, so what can we measure in this particular, what can we say about the nodal length in this particular context? So the nodal length for this particular ensemble, I guess it was initiated, the study in about 15 years ago by Isaiah Rudnik and Igor Wigman. And well, the nodal length itself, that it is proportional to the square root of lambda, is a rather easy computation using the Katz-Rice formula. But the variance in 2007, so Zaev and Igor Wigman, they suggested that the variance should be roughly, so n is the number, is a dimension of eigenspace, and that should be roughly of the order lambda divided by n. And actually, what happens in 2010 is that that lambda divided by n, this is a natural scale, and if you assume that there is no Barry's cancellation. And in 2011, Krishnapur, Kuhlberg, and Wigman, they actually spotted the fact. They proved that the variance is actually smaller. And to talk about the variance, so what they proved essentially is, I will need to define that. So to formulate the result, what exactly they proved, let me just talk about, maybe here, let me just talk about something which is very important for the torus. And this is really the distribution of the points, of integral points on the circle. So how would you characterize, so the points on the unit circle, if you look at this, okay.
We see some handwritten slides.
Yeah. This is my attempt to simulations. So let me just try to explain a little bit about what do we know about the integer points. So if I give you typical n, we know that the points on the unit circle, or on the circle of radius square root of n, the integral points, they tend to equidistribute. So we already agreed that there is there are quite a lot of them, some power of log. So there is power of log points, and they tend to equidistribute. And the fact that there is an equidistribution, in some sense, this is the result of Erdős Hall. But to understand the geometric picture, what dictates the geometric picture, one way to understand it is through the measures produced by the integral points. So what we're going to consider here is that, so for each integral point, what we can define is that we can define a probability measure, which just an average of the number, puts the delta masses of any integral points. So, and these measures will dictate the geometry of the eigenspace. And typically, as I said, as a byproduct of this equidistribution of the Erdős Hall results and Katai as well, for typical n, which has a normal number of prime factors, these measures converge to simply the uniform measure on the unit circle. However, there is another part to this story. And as I described before, there is our favorite primes. So the prime doesn't have equidistribution. The prime has essentially 8 different points on the circle. And another way to construct the measures that arise in this way is that what I might take is that I might take my favorite prime, and then I might take a prime with a very small Gaussian angle. So this, say, prime with a very small Gaussian angle, I could take it somewhere over here. So that will produce me, well, that will produce me 8 points which have symmetry. And then what I can do is I can cook up many of them by taking then several of these points and multiply them together. Then all these small angles will give me concentration about like some, well, in this case, I drew this concentration around the 4 poles. So another way, another extremal part of the measure, that geometric picture, is that you can have these, which are called Sartori measures, that he identified them about in beginning of 90s. So this is another type of the behavior of integral points on the circles. And as far as the measures that arise from these integral points, they have been characterized by Kullberg and Wigman in some way. But as far as the measure is concerned, so what I could do is I could take these measures and I could just start convolving them with each other. So, and if I just convolve them with each other and then take a closure as the weak star limit, then I will get a space of the measures that are called attainable. But to keep the picture in mind that everything is composed of sort of this compositions of the serial measures. And so this measures nu n, they enter the, so finally to state there, so to state this result that I want to talk about, there is this measure nu n that arise. And what characterizes the behavior of this measure is the 4th moment of this measure, the 4th Fourier coefficient. So mu n here is the measure that arises from the integral points on the circle. And I will remind you that S6, this is the number of these solutions which will enter. So what Krishnapur, Kullberg, and Wigman did is that they computed the variance, and they computed it, and the variance happened to be given by this expression. So it is proportional to lambda divided by n squared, not lambda divided by n. So there is this cancellation phenomena. And the error term here is given by precisely this number of solutions, which has been identified as the number of 6 points summing up to 0. And this has been, so if one can show that the number of the solutions is little o of n to the 4, then we know what main term is. And that has been actually shown. So this was the input of Bourgain at that time, that indeed the number of solutions is precisely little o of n to the 4. And Bombieri and Bourgain actually, so the conjecture is not known, but what they managed to show is that actually the exponent is 7/2 at that time. Okay, so with all these difficulties technical, I better move to what I want to talk about today. And this is something more fresh. So, and what I want to tell you about, I want to test another, not a Berry cancellation, but another phenomena predicted by Berry. And this phenomena goes back to, so far I've been considering all manifolds without boundary. And what Berry predicted in his 2002 paper, that actually if you put the boundary conditions, then it has to have an effect on the nodal length. So in particular, well, the nodal line is, if you think about Dirichlet or Neumann boundary conditions, then the nodal line is perpendicular to the boundary. And so he argued that this effect should be present, and he called it nodal deficiency. It actually has to have a negative effect on the nodal line. And what I want to do is I want to test, talk about testing this prediction on the, again, on the tori with Dirichlet boundary conditions. So now quickly the setup again that we've gone through before. So what is the setup here? So you've got a rectangle or square, and you've got a basic eigenfunction which respect the Dirichlet boundary condition, which is the product of signs. And here, yeah, the product of signs. And the Laplace eigenfunction corresponds to the mu1 squared plus mu2 squared, which is the sum of two squares. So this is exactly the same. And of course, now to get the eigenfunction which satisfies this condition as superposition, it's much more convenient. We already talked about that there is this natural symmetry to the points, that there is a natural symmetry with respect to the 45 degrees and also symmetries of the plane. So it's convenient to just quotient out our lattice by this trivial relations. And now if you want to define the nodal length, the boundary adapted arithmetic random wave in this context, then you could do exactly the same thing as we did before. So you take a real Gaussians and you take a superpositions of these waves and normalize according to the central limit theorem. The result that we proved with Igor Wigman and Valentina Cammarota a few years ago is that actually, if you compute the nodal length in this ensemble, then indeed what happens is that we do see the effect of the boundary in this case. So the effect of the boundary here is precisely this term that you can see here. And the solutions here, what happens is that, so this is asymptotic, so it had nothing to do with the integral points on the circles, except that there is this nu4 coefficient, which comes from the measure. And there is this error term, which is, we believe it's an error term, but this error term contains this quantity ML. So where the L now is not an else, but the number, so I'm coming to this question that I've described before. So the number of solutions to the equation when you project your sum down to the real axis. So instead of this equation before that we had that the sum equals to 0, now we have just the projection on the real line. So that's how the third or second type of question arises to that. So what we can see here is that there are two, let me see the time. So there are two interesting phenomena here which happens. So one interesting phenomena which happens is that the boundary effect here in the original manifold without boundary, the geometric quantity which corresponds to the points on the circles only enters when we compute the variance. So it hasn't been here for the nodal lengths. We just had a quantity which was independent of the geometric positions of the points. So in this case, already in the effect of the expected value of the nodal lengths, we see that the geometry enters the picture. This is one way to see that. The second thing is to notice is that so the deficiency naturally for typical n, nu4, the coefficients nu4, it's actually very close. They converge to 0 because they converge to the uniform measure. So for typical eigenvalue, for typical energy level, what happens is that this coefficient is 0, and what you have is that you have this minus the geometric quantity 1/16 times 1/n. So you have this nodal deficiency with a negative sign, which is predicted by Barry. But I didn't tell you before whether we can estimate these error terms and what is the theorem. And I will tell you that after I state another result, which has to do with the following. So what we said in our study at that time is that, well, so you can see that the effective boundary here is of the size of the fluctuations of nodal length. So it only enters with the factor of 1/n. So if you would like to sample, if you want to detect it numerically, say, or if you would like to see this effective boundary, there are two ways of doing that. Because it's of the size of the fluctuations, you can either take many samples, or you can take and measure your nodal length in the vicinity of the boundary, where the effect, Barry predicted the effect of the boundary closer to the boundary should be stronger. So what we decided to do with Andrea Sartori is to understand the distribution of the nodal length in the shrinking balls on the Planck scale, hoping that you can see the effect of boundaries there, in there. And oh, yes. So let me just state here, because I'm not entirely sure how much time I have left, but let me just state another theorem in this realm, is that what we proved in this year with Andrea Sartori is that the strengthening of this result. And the strengthening consists of the following. So if you take a nodal length and restrict it to the shrinking ball towards the Planck scale, so when you're roughly at the square root of the wavelength, then the asymptotic behavior still propagates. So the same asymptotic holds, and the same asymptotic holds for the generic n. So not for all energy levels, but for the proportion 1 of the energy level. Here what you can see is that actually this nodal length, it is exactly the same asymptotic behavior in the vicinity of the boundary or inside the manifold. So you don't see the difference. It's a uniform effect of the boundary in the entire space, in the entire manifold, which was a bit surprising because in the original Barry's model, you can see that the further you go from the boundary, I guess, the smaller effect is. And in this case, so all these type of theorems that I told you about before are the consequences essentially the following, that of the following equidistribution of the points of the solutions. And what exactly we prove about the points is that if we take a generic n, so for the proportion 1 of admissible n, that are sum of two squares, the number of solutions to all these three problems that I've described before. So either this is the shrinking, that the sum of all the vectors is slightly smaller than square root of n, or it's exactly 0, or this is projection on your favorite direction is smaller than the expected. So what we proved is that it's only the diagonal behavior. So the only way to get it, the number of solutions, is roughly take some points with a plot with k points as you wish, and the rest k take minus your points. So this is basically as far as the results go. So you can see this results, the effect of the boundary. So I don't have much time to tell you more about what is the reglement of how much time do I have?
You can have up to, say, 10 minutes more if you want.
Okay, so then I'd like to tell you a little bit about perhaps two things. So first of all, I want to tell you why is it possible to prove that these solutions do occur, why they're all diagonal, and what is behind this, all these results in a couple of words. And perhaps mentioned one more instance completely unrelated where this technology can be applied in the analysis context. So how would you prove, how in general those results are proved in the context computing the nodal length? So the key things, there are two key things. The first one is the Katz-Rice formula. And the Katz-Rice formula, so I don't have much time to talk about this, but the Katz-Rice formula essentially tells you that in order to compute the nodal length, it's enough to compute the integral of this intensity function. And what is this intensity function? So the nodal length, it's a very general phenomenon, is given by the integral of the expectation of the gradient conditioned on the fact that your field is zero. And so this is the key in all the applications that I've been talking about in this work and in others' work. And because you're working in the Gaussian case, so these kind of correlation, these expectations could be converted into computing some certain quantities in terms of covariance matrices. So in two words, I want to tell you where these equations arise on the units, the equations, additive equations for the points. So of course, if you look at the covariance matrix, and if you think about that, so if you expand everything before, roughly speaking, in terms of Taylor coefficients, then you will get the moments of the covariance function. And if you look at the moments, then over the small balls, then of course, if you, this is just simply the moments, the moment computation will just give you naturally the powers of these points. And the main contribution, if you believe in heuristic, should really come from the points for which these quantities are unusually small. So if you look at the distribution of, well, precisely equal to zero. So when they precisely equal to zero, you don't have any cancellation in the, of course, in the exponential phase. But if you're studying this, our problems on more refined scale, on the Planck scale, then what will also contribute are not just into the moments, and not just the points where you exactly sum up to zero, but of course the points where you're very, very close to zero, below Planck scale, somewhat below the Planck scale, or at the Planck scale. So this is a very rough heuristic, because I don't have time, of why these points, these additive equations appear there. And in the next couple of minutes, I want to tell you a general fact. Why exactly can we solve all these equations on average in a couple of minutes, at least on heuristic level. So here is the setup, how you would look at these problems. So well, suppose I want to solve my, before I tell you how to solve such equation, in 3 minutes, I want to describe the content of 10 papers, but the basic idea, how do you construct the points on the unit, on the circles, integral points on the circles, is that what you can do, you can take your favorite n, which is a product of prime factors, and which are all 1 mod 4, you can assume right now. So let's take a very generic situation. And so what you can do is you can decompose your prime factor we said that there is a unique way of decomposing it as the product of the Gaussian primes. And then any point on the circle of radius square root of n will look like some rotation factor, which doesn't matter, times the product of these pi i's. And these pi i's, from each pi I, you can take either prime, Gaussian prime itself, or the conjugate to it. So that's how you build up all the points on the circles. And now imagine that I have an equation. So I have an equation of these points, which happen to add up to 0. So if I have such an equation and I look at the prime factorization, if I look at the prime factorization, then as I told you before, you can take either pi k or pi k conjugate. So what I can do is I can write down this equation, and from some of this new I can factor out the pi k's, and from some of them I can factor out pi k conjugate. And the key idea in all these applications, for almost all, is the fact that now what I have, if I give you k minus 1 first primes, then these quantities are completely determined by the values of your k minus 1 primes, because they don't depend on pi k. And from this equation, pi k is determined uniquely. And this is not what is happening, or roughly, this doesn't happen for typical integer. So for typical integer, if you look at the prime factors of typical integer, the kth prime factor, the largest prime factor, is completely independent in terms of additive relations from all the k minus 1 factors. So, and this is what the anatomy of integers tells you. And in case of these equations, if I have here equations, which I've talked about before, if we look at the not exact equality, but if we look at the equality where the sums cancel somewhat, or the projections, what this will tell you, if you fix k minus 1 divisor of this, that the k prime factors is constrained in some angle, which also doesn't happen for typical integers. So all these results are the consequence, in some sense, of the fact that the main idea of the proof is to show that this is inconsistent with the typical anatomy of integers. And I guess, well, I have more application to that, which has to do with random multiplicative functions, but I will not talk about that. I will just stop and thank you all of you for attention.
Thank you for the talk. Who has a question?
Oleksiy, if you study higher moments of, let's say, lengths of 0 lines, do you get solutions of, do you look at like 8 tuples and 10 tuples and so on?
Sorry, if you study,
if you look at I don't know, even moments of the length, of the length of nodal line of random arithmetic wave, do you get, you know, 8 tuples of points that sum to 0 and then 10 tuples and so on, or
yeah,
not?
so if you study higher moments, you will get, of course, the higher moments of covariance, you will get the higher tuples, but also, so it's interesting actually question about that. So the what happens in the central limit theorem, so what you would expect is that you would, if you try to prove the central limit theorem, for instance, then you would want to study the higher moments of the, not just variance, but the higher moments of the nodal lengths, and hope that they would match up the distribution. So it has been, so central limit theorems have been established, but in the case of length, actually doesn't converge to Gaussian, so it's not determined by the moments. What it is determined by, though, is the so it has been proved, like what is used fourth moments methods, and namely the Wiener chaos. So the distributional results are not proved by computing the higher moments, but rather proving the fourth moment estimates and showing that the projections on the the fourth component dominates. But I guess, yeah, so you will get higher correlations in this study.
Yeah, and I guess it's a small remark that these n tuples, of course, appear if you study LP norms of eigenfunctions on Tauri, and also Bourgain and other people thought about that.
Right. So this is the type of literature that I completely ignored. Of course, is non-random parts, and ignored right now is that. Indeed, and Zygmunt's motivation also to consider this was exactly studying the higher moments of the just the trigonometric polynomials.
And I guess a conjecture is that this L6 and whatever that should be uniformly bounded for all n, right, or something like this. That could be a conjecture.
Yeah, well, I mean, this is essentially in the case of this is essentially equivalent to the conjecture of L3 norm is
so this is equivalent to basically this the main contribution coming from diagonal.
Yeah. But here I'm only looking at the frequencies that are sum of two squares.
Yeah, of course. Thanks.
Yeah. So
no, in my thesis, I have a small weak generalization of this lemma of Cook and Zygmunt about uniform bound for L4, but it doesn't buy you anything good if you look at the LP norms. Unfortunately, it's weaker.
Right. So the thing that this universal phenomena is actually it is quite universal. I haven't talked about. There is a very nice related to LP norms. This is a very nice result, a very classical result of Salem and Zygmunt, that if you take a random trigonometric polynomial, then there is a Gaussian distribution, and you also know that the maximum is proportional to square root of log n, like in iterated laws of logarithm, but when you sample on the points. And there was a very nice result of Benatar and Nishri and Rogers, which established the same behavior, central limit theorem, for coefficients being random multiplicative function. And actually the observation, it's unpublished, but actually you can use this technology of this phenomena of computing the solutions and then diagonal domination is actually this technique can be applied to the curves, not only for the circles, but say the curve x log x. And in this case, it would also give you Gaussian distribution of this object of the random trigonometric polynomial with multiplicative coefficients. Studying these equations, it's a rather general phenomenon. Of course, it has to do with decoupling and so on and so forth.
Thank you. Does anyone else have a question?
So I was wondering, when you were talking about the nodal lengths for the Dirichlet eigenfunctions, you said that it holds for almost all n. Is it a technical artifact, or do you actually have sequences where it fails?
Yeah, so as far as the boundary, so this is what again, as I'm saying, as far as in our results for the manifold with boundary, for the manifold without boundary, it actually holds for all eigenfunctions, and this was the result of Krishnapur, Wigman, and Kuhlberg. There is no restrictions. It holds for any energy level. And for us, it is a very much technical artifact. It's a wonderful question. So this theorem with Andrea that there is diagonal domination, it also should be that it should hold for every single n. And then we would get a result for all energy level. Not only this, we are so Bourgain was able, Bombieri-Bourgain and Bourgain himself, so he was able to show that the trivial number of solution on the 6-tuple equation is n to the 4. And as soon as you get little of n to the 4, you immediately get that your result, your asymptotic holds for any energy level. However, in our case, we can't save even a little bit, not to say even the asymptotic behavior, but even a little bit, little o of n to the length minus 2. We don't know how to do it. So even a little bit of saving, not proving the entire conjecture, would have been enough to say that everything holds for every energy level. It's a long answer to the, yeah.
It's a long answer, but it does answer the question.
I like those questions that I can answer.
Does anyone else have a question? Please feel free to. Well, I guess in that case, we can thank the speaker again. Thank you for the talk.
Thanks a lot, Oleksiy.
And we meet again next week for a talk of Gregory Beck-Kolaiko on towards more theory of dispersion relations. Have a nice evening.
Thanks very much. Have a good one.
Thank you, everybody. See you all next week.